Right, so what I would like to tell you now, how to derive a Hamiltonian static from symmetry principles. And I will show it using in case of the irradiate. And after that, I need to think. It depends how long will this last. Then maybe I will tell you how to see, how to find out the interaction between the spins and electric polarization. Then maybe I will talk about quadruples and nematic ordering. But definitely at the end, I would like to show you how to observe quadrupolar waves, quadrupolar spin waves in some spin systems. Right, so let's start. We start with the irradiates. And here, first, I will sketch you the crystal structure, the main building block of the crystal structure. For that, I need different colors. The colors are here. I thought first to draw the drawing on the other part, but maybe this is better here. So I would like to draw edge-sharing octahedra because the iridium sits in the middle of this edge-sharing octahedra. So maybe like this. And maybe the blue one is the back side of the octahedron. Right, so can you see it from the back? Yes, you can, good. Is it right? Did I use, okay, so these are actually all green, huh? Okay, they are all green. So you're saying that these colors look the same to you?
But that may be my problem.
Okay. Right. And then in fact, there is behind the triangle that we don't really see. And in the middle, there are the iridium ions, which are magnetic, here and here. Actually, this structure, they make a honeycomb lattice. So in fact, I would need to continue here, and this is important because this tells us the whole structure, tells us what is the symmetry of point group and space group. So like this, then let's continue here. Okay, this is getting at, yeah. Let's see. Like this. Okay, these are distorted octahedra, but in reality they are all fine. So, and here we have the iridium ions in the middle. And certainly it continues that way. It must be clear, right? Like this, and then the next one. Right? And then you can see here. No, mistake. Forget it. It would stick to. Right, let's correct it. Come here, the next. I'm sorry for mistake. Like this. Okay, so can you see the three-dimensional structure? What I draw. So these are octahedra. They are touching at the edges. Okay, good. So what are the symmetries of this object? So we have a C2 axis. The middle of this bond between two iridium ions. Is an inversion center. There is an inversion. And there is also a mirror plane that is perpendicular to the plane that I have shown, and it is also perpendicular to the bond between the two iridium ions. So the symmetry group consists of unity. There is the C2, there is the mirror plane, and there is the inversion. We need to specify how different quantities transform. We also need to draw the coordinate axis, and I will choose the following coordinate axis. Starting from the center of the hadron, the coordinates are looking towards the upper corners of the hadron. So there will be the three axes like this. They are slightly tilted toward us. I cannot draw that. Maybe I can like this. And say this is the z-axis, this is the x-axis, and this is the y-axis. Right.
Is there a rotational symmetric C6?
There is a C6, absolutely. Right, thank you. I will also draw it with this color. Yeah, okay, let's put just D6. Actually, it is D6 or whatever. Right. The D6, I didn't care about C6 because what it will do, it will move this bond from here to here. So once we know the Hamiltonian on this bond, it will tell us what is the Hamiltonian on these bonds and so on. Right. Okay, so I have site 1 and 2 here. So this doesn't do anything to sites 1 and 2. The C2, it makes a rotation around this link. So the 1 and 2 will stay where they are. The mirror will exchange 1 and 2. So 1 will go to 2, and side 2 will go to 1. And inversion, of course, it also exchanges sides 2 and 1. Then we have the x, y, z operators, and we have the Sx, Sy, Sz operators. What does happen to these quantities? So inversion is just all the coordinates will go to negative, will get a minus sign, so x will go to minus x, y will go to minus y, and z will go to minus z. The C2 will rotate this coordinate system, so C2 and z are the axis of the C2 rotation and z, they are orthogonal to each other, so the z will go to minus z. If we rotate this, then x will actually become minus y, and y will become minus x. I hope it is correct. So you just take the cube. I mean, this is like having the three edges of a cube and you rotate by C2, then you will see that this will happen. A mirror, what does the mirror do? It will leave unchanged the z. And now we need to figure out, I didn't do it at home, I did at home this part. This now, I think the mirror will just change x to y and y to x. Yes, like this. Okay, what happens to the spin operators. The spin operators are axial vectors. They behave differently. So you can think about them as you have something that rotates like that. And if we make a mirror, okay, let's start with inversion. So inversion, how does inversion work? So anyway, inversion will not change the spins. It will not change the sign of the axial vectors. Mirror plane, here, if we have an SZ, then if this is the mirror plane, and then I start to rotate my things, this is in the mirror, you see that if this is pointing up, the other will point down. So here, I will get a minus SZ, and what happens for the other ones, I will just read it off from here, hoping that I didn't make any mistake. So apparently they will, Sx will go to minus Sy, and Sy will go to minus Sx. No, not here. Minus, minus, yes. Ouch, ouch, ouch. Ouch, ouch. No. Minus here, good. Right. The C2 will have, C2 will just rotate, so S, actually for rotations, the spin and the axial operators, they transform the same way, so it will become minus Sy and minus Sx. Right. I hope this is fine. And now let's try to find what the Hamiltonian can be. So Hamiltonian we can write as J alpha beta S1 alpha S2 beta. And this Hamiltonian needs to be invariant under the generators of this group, under the action of this group. How to do it? The simplest thing is that we take a trial state and we apply one of the elements here and another element here, another element here, and add the map. Because if we add the map with equal weight, this will be the invariant of the group. Right, so let's try to do it. The simplest thing is with the inversion. So this we can write, there is the J alpha beta as written here, maybe this is S1x, S1y, S1z, S2x, S2y, S2z, and these are the elements that I just called A, B, C, D, E, F, G, A, H, K. So this is JXX, JXY, JXZ, and so on. I'm just lazy to write many. Is it fine? Yeah. Right, okay. So what does the inversion do? Inversion does not change anything. It does not change the spins, but it changes 1 and 2, the spin 1 and spin 2 index. So after inversion, this 3x3 matrix will become, but we need to transpose it. Index 1 goes to index 2 goes to index 1. So this is just transposed. You are shaking your heads. Okay, sorry, I thought that I made some mistake. A, B, C, D, E, F.
Actually, why did you go to K after H?
Excuse me?
Why did you go to K after H? So it's G,
E.
H.
No, you're right. I forgot about the AB. I mean, you know, when you are in front of the blackboard, you forget the obvious things. Right? G, H, K, okay, sorry, yes, right. Good. And I need to add them up. If I add them up, it will be something that is, we will have two A's here. We will have B plus D here, B plus D here, 2E, 2K, 2C plus, sorry, G plus G, F plus H, G plus C, and H plus F. Right. So what we observe, that if there is an inversion center at the middle of the bond, then this J alpha B matrix becomes symmetric. If it becomes symmetric, it means that there are no terms like D times S cos S in this Hamiltonian, because they would correspond to the antisymmetric part of this matrix. Okay, so whenever we have a bond which has an inversion center, it has no Jaroszewski-Moria interactions. That is a very important rule, a very simple one to remember. Okay, so we are left with this symmetric matrix, and this came after applying the inversion symmetry. Okay, so now I would like to make it simpler. So since I run out of space, then we know after inversion we have 1 and inversion. What remains is a symmetric matrix. So I will just rename these matrix elements. I can delete all this here. And then my task is much simpler because I just need to remember much less element A, B, C, D, E, E, C, F. Like this is easier now. So this is a symmetric one. And let's apply now, say, the C2. I apply the C2 because there is no need to exchange the 1 and 2 here. So what C2 does is that it will change the sign of SZ. Actually, all of them get a minus sign. So if I multiply by minus all the rows from here and all the columns, it will not change anything. So this minus sign is not important. What is important that it will exchange these two columns and these two rows, because Sx will go to Sy, Sy will go to Sx. So I need to add D, B, B, A, E, C. You see I exchange this here and that one there, E, C, F. And what I will get is 2A, 2B, E plus C. This is D. This is long here. A plus D, A plus D, 2B, E plus C, C plus E, C plus E, 2F. Okay? So I got that these two elements are equal. This is different. There are these two elements and there are these two which are also equal. Just for convenience, I will write them here. So it would be like some, let's use capital A's so that no. I will use J, gamma prime, gamma prime, gamma prime, And here I will use it J minus. No, I will use what? K plus J. Right. Okay? Is this fine? Explain which step?
The second matrix.
This one? Right. So what I needed to do is that here I had Sx, Sy, and instead of Sx, Sy, it changed to Sy, Sx. So I had a Jx something, Jx alpha, Sx S alpha, it changed to Jx alpha, okay, S alpha, Sy, S alpha. Of course, I need to take care of also alpha. So, and it means that when the matrix element was somewhere in the first column in this matrix, this was the Jx alpha. Now it becomes the second column because it's now multiplying the Sy. So it will just move over here. And this is the after applying the Sx to Sy. And similarly, Sy here becomes Sx, so it will just swap these two columns for spin 1, and similarly, I need to spin swap the two rows for the second spin as well, the x and y. Is this clear, or would you like some more explanation? So, or? Yes. Okay, good. Yes, right. So this is what I ended up with. And how does it look like writing the full form? The Hamiltonian is just J times S1x times S2x plus S1y times S2y plus K times S1z times S2z. And obviously, it's not by accident that I have chosen the J's here, because this will be the Heisenberg term. Not like this, plus the K S1z S2z, plus there will be other term, which is gamma times S1y S2x plus S1x S2y plus gamma prime, and here I need to put S1z plus S1z times S2x plus S2y plus S2x plus S2y, one here, one, S2z. Okay, so this is the most general symmetry allowed Hamiltonian for this bond in this lattice. And similarly, we can work out how it looks like for the other bonds. Since Z was orthogonal to this one, here the y-axis is orthogonal, then it is easy to deduce that what we will have here is the K times Sy. So what we got is the Heisenberg part and an isotropy that is exactly of Kitaev type. And we got some additional elements. Now, there was the suggestion that indeed in this type of iridates, the Kitaev and Heisenberg parts are competing with each other, one favoring some antiferromagnetic state, the other one favoring the liquid state. And in 2009, Georgia Kelly and Guignat, they derived this type of Hamiltonian starting from microscopic model, starting from really looking at the orbitals. Later, it became clear that the simple Heisenberg model plus Kitaev model is not enough. We need additional terms to describe the actual materials. Actual materials are of the form A, iridium O3. I think the A can be not sodium or strontium. And there is also another material, alpha ruthenium trichloride. They all have the same structure, and they all have the same type of Hamiltonians. And it appears to describe the Newton scattering experiments, one needs to add this gamma and gamma prime symmetric couplings, and also maybe second neighbor and third neighbor exchanges. Right. So this is how to derive a Hamiltonian starting from symmetry principles. Are there any questions related to this?
So, typical irradiate, what are the relative strength of these different terms? In a typical irradiate,
Yes?
what's the relative strength of these different terms?
Right. Come on. Very good. Maybe I closed it. I may have closed it. I'm sorry. Okay, so this is the Jacqueline paper, and I had some, I checked, there were some recent papers in arXiv and so on. I can look it up. Nevertheless, these are too strong, apparently too strong too strong for pure Kitaev physics. So eventually the material is in the part of the phase diagram which orders. At the same time, the Kitaev physics seems to appear in the excitation spectrum in the higher energies. Right. So you just, Google search irradiate or this material and Kitaev and Heisenberg on the arXiv, and I think one of the recent papers is Jose Valenti. Yes, maybe I can give you a reference once I find, where is my note? Here's my note. So for example, this is the last one, at least a recent one, and I think they refer to all other papers. So this is 1702, arXiv 08466. They do ab initio calculation or some quantum chemistry calculation to derive these numbers. And I think they don't show one of the gammas, but they have J3s. And in some of the references, there are some other papers where these gammas are present. In some cases, there is a minus sign somewhere. It depends also how you define your coordinate system and so on. Right. Good.
Karlo.
Yes, please.
So, is there an estimate of gamma over k?
I think this is the same question that it was here. There is an estimate, but I don't know what is the estimate, what is the value. So I can look it up, or you can just go to arXiv and check it here. Right, so they give some ab initio estimates.
You didn't use the mirrors, right?
Hmm?
The name. The second one, the name.
This one, this. Eh?
On the name one, you see you and
I think it gets because of the mirror symmetry. The Z doesn't get the minus sign.
Saying you derive the Hamiltonian.
Yes?
You used I and C2. But you didn't
Oh, yes. Okay, that's right. I didn't use it because the inversion time C2 gives M. Yes, so I could use it, but it will not produce anything new. You're absolutely right. Thank you.
Yeah, I have a question.
Yes.
Yeah, in the second term you are saying that is the Kitaev term. It looks Ising to me. Is it because of the C6 symmetry?
I think this is the Kitaev term. You have on this bond, the Kitaev, I mean, this is just for these two spins.
Yeah.
And the Kitaev model is just that along this bond, we have the SZ. Along this bond, we have the SY. And along this bond, we have the SX.
Yeah, so in that case, there is no possibility of a Ising Hamiltonian on that iridate?
No, if you look at only this bond, indeed you are right, it looks like an Ising-like term. But when you go over to next bond, it will change the axis, and instead of having the...
No, that I understand. Now, what I'm asking, is there a Ising Hamiltonian possible on that iridate?
Ising in what sense?
I guess the question is that with this symmetry, can you just have a
No,
SZ?
you cannot. You mean SZ, which is the same for every bond? No, you cannot. Because I mean the SX, I mean here, this is the form that they need to go together. So if you make them 0, and if this is only finite, this will change once you apply the C6 rotation that Ganesh asked for. So you have this Hamiltonian 4 bond, and you apply the C6, and they will change the Ising, local Ising axis from Z to X and Y. Good. So let's go further. Now, I would like to apply the same symmetry argument to a different case. Yes, before doing that, remember that this was not a symmetry group of a honeycomb lattice, a pure honeycomb lattice. We needed to take into account that this was a lower symmetry. So some of the mirror symmetries that are present in just a pure honeycomb lattice, they were not present here once we added the oxygen environment around the iridium atoms. Right, so let the next problem be the following. I'm just drawing the cube. In the middle of the cube, there is some magnetic ion. In this case, it is a cobalt. It has a spin that is 3/2, so larger than spin 1/2. And the environment is tetrahedral 1, so it means that we have oxygens on only 4 corners around it. So I just need the cube full. So here's another oxygen. So it is 4, its coordination is 4. It is surrounded by 4 oxygens in a tetrahedral environment. It means that the symmetry elements in this case are the tetrahedral group TD. The TD is the so-called achiral tetrahedral group or full tetrahedral group. Achiral because we will include also the mirror symmetries. It was 24 elements. And in fact, it is isomorphic to the S4 symmetry group. It consists of 8 C3 rotations around this axis. It will have 3 C2 rotations around the 1, 0, 0 axis, around the X, Y, Z axis. There will be 6 mirror planes. Here, I mean, you can easily see that we can just mirror the tetrahedron when the mirror plane contains one of its edges. And there will be 6 operations that are called S4. This S4 is not this same S4, so maybe I write it like So this is some written S, and this is just simple S4. It means a C4 rotation followed by inversion. Right? So if we have a tetrahedron, I draw it from above. If we apply a C4 rotation, it will go over to 1, 2, 3, 4, this here. So this is not the same tetrahedron, but if we apply inversion, it will become, the bond which was on the top will go to the bottom, and what was on the bottom will come up. This will go down here, this will go here, this will go here, this will go here. So this is an S4. So this is a C4, this is an inversion, and this is a S4 symmetry group element. And that is this here. We have 6 of them because we can define 6 of those axes where we first rotate by C4. There are 6 faces of the cube. But we can observe that here the inversion is missing. It is not here. Inversion is not here. It's very important. Why is it important? Because it will allow the spin to couple to a usual vector. So to couple axial vector to usual vector. Usual vector is like electric field or polarization. So the spins are able to couple to a magnetic field, to electric field in this tetrahedral environment. Why is it possible? So, what would be coupling between the spin and electric field? So, usually in Hamiltonian, we would like to have something which is P times P. There are some coefficients again here. Let me don't put any indices yet. So, can we have such a term in Hamiltonian? If it is time universal invariant. We cannot, because if we apply time universal invariance, the S will change to minus S. So we need to have 2 S's. S needs to be on the square. Can the P be alone? If there is inversion symmetry, the inversion symmetry does not change the spin, but it will change the P to minus P. So if there is inversion symmetry, this term is not allowed. But if the inversion symmetry is absent, in that case, this type of terms is allowed. And if we go through all of these elements here, that I will not do here because it's kind of lengthy and the time is running, in that case we will find out that we can add to the Hamiltonian the following term.
So E is like the polarization.
Yes, this is electric polarization. That couples to electric field, or we can couple this directly to electric field if you wish. Let's do it. Let's do it that way. So this is electric field, so that it's easier. So what is allowed is the following form. Ex times Sy Sz plus Sz Sy plus Ey Sx Sz plus Sz Sx plus Ez times Sx Sy plus Sy Sx. So in other words, the electric field vector Ex Ey Ez is proportional to Sx Sz Sy Sz. I put a bar over there. The bar means symmetrization. Sx Sz and here Sx Sy. Right. So if there is a finite magnetization in the cobalt, it will induce an electric field. How will it induce the electric field? The spin-orbit coupling will, in this case, modify in the presence of some spin orientation. It will modify the electronic wave functions within this tetrahedral environment, and the center of gravity of the electronic wave will move in certain directions, kind of, and that will, relative to the cage, and that will produce an electric polarization. So this mechanism is due to Arima, and maybe I think he derived it like less than 10 years ago. Right. Why is this interesting? It is interesting for the following reason. Yes?
Here, where do the spin operators sit? Where does the electric field sit?
All on the same side. We just look on a single tetrahedron.
On the cobalt. So
On the cobalt, just a single ion physics we looked. Right. So, what probes do we have? We have neutron scattering. The neutron scattering will interact with the spin dipoles. We have ESR, and we have infrared absorption. Now, ESR and infrared absorption is interaction of light with matter. And the light has electric and magnetic component. The magnetic component of the light will interact with the spin dipoles. If we have this coupling between the electric field and spins in the multivariate compounds, it becomes possible for the light to interact with the spins, actually the spin squares. And if we look at, for example, this case here, so the light has an EZ component, and if we write this using the S plus and the S minus operators, it will turn out that it will be EZ times S plus, maybe minus S minus S minus. So this term is able to produce two Magnon processes. And that's why, for example, two Magnon excitations will become visible. Right, and I will show you an example for that. Okay, in a minute. Are there any questions related to this part?
you mean if you shine light, then one photon can excite two magnets?
Exactly. So there are different configurations. So usually the experiment is performed under magnetic field. So it depends on the details. There is a magnetic field, and then the propagation of light can be parallel to the magnetic field, or it can be orthogonal to the magnetic field, and they can, there's some Faraday and Voigt configurations. It becomes complicated, and there are different matrix elements, polarizations, and so on. And this complication you can turn to your advantage, because if all of those, you have many different, relative to the magnetic field, many different polarization, incident k directions, and many different matrix elements you can calculate, and they all match from a calculation with the experiment, then I think you are happy. You did your job. And then you can go to publication. If there is a problem, then you need to scratch your head, and then you ask the experimenters, maybe they screwed up the measurement, maybe they screwed up the axis, or maybe you made a minus sign error, whatever. Okay, right. Good. Further questions? No more questions, then let's go further. So what is the material we are looking at? The material is, this I don't need anymore. This is the material here. Over there. Strontium 2 cobalt germanium 207. It is a member of a bigger family. Instead of strontium, I forgot the members of the family. Instead of strontium, you can use barium, or maybe even calcium. Instead of germanium, you can use silicium. But the cobalt oxygen stays. These are the magnetically active ions, and they have the spin equal 3/2, as I told you before. The crystal structure is shown on this plot here. And what you can see here is that the cobalt ions, if we continue this, the cobalt ions make a square lattice. So this, and this material is a layered material. So we have layers of squares. And in each square, there is a spin 3/2 sitting. They are interacting antiferromagnetically. So they will have an antiferromagnetic Néel order. Furthermore, you see these blue things here. I don't know if you can see it nicely or not, but let's try to make it bigger. Right? Yes. So what you can see here is the tetrahedra. And in the middle of the tetrahedra sits the cobalt ion. So, and they are tilted with respect to each other. So it's not the unit cell contains 2 cobalt ions. Okay, so this is the material we are looking at. Maybe another picture of this guy. What is this? No, yes, is it? Yes, sorry, coming back to one of the earlier questions about the values of gamma and K and J. Sorry, this was the paper I was looking for and I didn't find it. So this is the archive version this is still the Kitaev problem. Here is the Hamiltonian, J1, K, gamma. They only take 1 gamma, and these are some calculations. And I don't know, model 1, J 2.2, K 7.4, gamma minus 2. Okay, this is slightly different. Yeah, I don't know. Anyway, you find some numbers here in this paper. Right. Yes. I didn't read carefully this paper. So I don't know what they compare. But anyway, right, you see that there are these numbers in this paper, and also maybe, yeah, what is this here? This is different. This I won't talk. This. Okay, good. So here we were. This I can close now. Yes, this here. This is the same plot, less artistic but easier to understand. These are the tetrahedra that are tilted with 2 different angles with respect to each other. What are the other interactions in the Hamiltonian? We can do the symmetry analysis. There will be many different parts. But what appears to be the most important one is the following. There will be J times SA times SB dot SB. This is a Heisenberg interaction between the neighboring spins. There will be on-site anisotropy, SAZ square plus SBZ square. There is the effect of magnetic field. And we can write the E times S times S. So I don't write how it looks like. It's quite nasty, but there is the interaction between electric field and the spin particles. So what do we expect at 0 field? This is antiferromagnetically ordered. Right. If we turn on a little bit of magnetic field, the spins will become perpendicular to that magnetic field. So if we rotate the magnetic field, the spins will rotate themselves with the magnetic field. Right, good, excellent. So there was this single tetrahedron, and so how was it? We just need the, so the spins is moving in the x and y, this is the z here, x and y, so I think ex, ey, ez, I think there was a y as z, there was a sx as z, there was a sx as y. We don't have a z component, this is absent, this is the only one that survives, and it has the form sx times sy. So if the spin is pointing like this with respect to tetrahedron, there is no electric polarization. So let's do it. Right? Let's write here. 1, 2, 3, 4. Direction of the spin like this, like this, like this, like this. So I'm rotating the spin in the plane. And with this green color, here there is no magnetic field, no electric polarization. If the Sx, Sz, Sx, Sy, they have both components here, so this will become finite. There will be some electric polarization. When I am here, again it disappears. When I am here, the polarization will point upwards. So what happened is 0 up, 0 down. And again, when my spin is back, is just opposite to where I started from, it will be again 0. So making a half turn, the polarization made a full cycle, up and down. So making a full cycle, the polarization will go up once, twice, once, twice. Okay, can we see this? Yeah, it's not this. I need to look for a different slide, different paper. My docs. Let's go to docs. My excuse for is there any talk here? I hope there is something here. Let's see what is this here. No? Maybe here? Come on, come on, come on. Yes, there it is. I don't cancel, don't convert movies. Hello. What happened? Okay, so what I want to show you is an experiment where they did exactly, yes, right, very good. And I'm sorry. So what you will see is that theta dependence, when theta is going from 1 to 2 pi of the electric polarization along the z direction or along the 0, 0, 1 direction, and it will show exactly this oscillation that we expect. Right, there it is. So the theta angle, not theta, phi angle, phi h, goes from minus 90 degree to 270 degree, and this is the polarization that that has been measured along the c direction, along the z direction. So it does exactly what we figured out here. It's slightly, yes?
Put an external electric field that changes direction.
No, so we have antiferromagnetic nil state. The antiferromagnetic nil state, you have the two spins that are pointing oppositely. We add an external magnetic field. If the magnetic field is pointing that way, then the nil state will turn itself orthogonal to the direction of the field. And then we rotate the magnetic field. The two spins will follow the magnetic field, and that's how we can control the direction of the spins in the tetrahedron. So, yes, thank you.
In this case, it's also antiferroelectric.
Sometimes, yes. So what you measure, okay, it's right, very good question. So we have the two tetrahedra that are slightly disoriented with respect to each other. So as we turn the spins, in some case the polarization will be antiferroelectric. That is happening, right, in some cases it will be cancelling each other, in some cases it will be just zero, and in some cases there will be ferroelectric. So taking all this into account, you still end up with such a line over there. So what is important is that if we turn once around, we make two sweeps up and down, and that tells us that whatever couples to the spins is somehow square of the spin. Whatever couples to electric polarization is square of the spin. So, okay, let me, coming back to this question, so maybe this is the direction of magnetic field and this is the spin. And this is one sublattice. And then there is the other sublattice with the slightly disoriented tetrahedron, and there the spin is just pointing in the other direction, and it will have also some polarization component that I don't know the value exactly. And here it will follow. Any questions? Good. Right. So this is what this material does, and there is this D factor here. So we would like to describe this material, and this is a spin-free half. So what we do exactly what I told you in this morning, just try to look at this factorized wave function, because probably the spin is free half, maybe that is enough to describe the problem. And this D is an easy plane anisotropy. That is important. Right. Easy plane anisotropy, it means that the D is positive. We don't like the spin to be in the Z direction. So, okay, so how do I describe a spin that is in the XY plane? We have four spin components. We have the plus, if we work in the SZ basis, there is a plus 3 half, there is a plus 1 half, there is a minus 1 half, and there is a minus 3 half. So if we would like to describe a spin that is pointing in the x direction, so what we would do is to take SZ equals spin 3 half component, and using the rotation matrix of the spin 3 half rotation matrices, we will turn it by pi half over the around the y-axis into the x direction. If we do that, what we get is the following. It is a 3 half component plus square root of 3 times 1 half component plus square root of 3 times minus 1 half component plus the minus 3 half component. So this is a spin that is pointing, in the direction of the x-axis. Okay, let's put it this way. This is not the best notation, but it will do for the moment. So here the spin is pointing along the x-axis. However, if it wants to do that, then this D will punish the 3/2 and the minus 3/2 spin components to achieve perfect optimal conditions to satisfy both the antiferromagnetic and the easy plane anisotropy. The good on-site solution will acquire additional eta parameter, which will suppress, in fact, this 3/2 with respect to spin 1/2. So the wave function that we will end up with will look like the following. There will be the 3/2 plus minus 3/2 plus eta times square root 3 1/2 plus minus 1/2 component. And this eta will be a finite number larger than 1, larger equal 1, if d is larger equal 0. So if d is equal to 0, there is no easy plane anisotropy. In that case, eta is equal to 1, and then this is a SU2 symmetric problem, or O3 symmetric, so there is no problem to turn the spin in the xy plane. However, if there is a d, there is a price that the 3/2 needs to pay to satisfy the constraint. So, excellent, but if we start from a spin coherent state or fully magnetized state, spin state, like X, and we rotate it, if this eta is equal to 1, we have a fully stretched spin. If eta is different from 1, it means that if we calculate the length of this spin, it will be shorter than 3/2. So what will happen is that the spins are kind of shorter. So if we apply magnetic field, what happens is that, okay, so the spins are antiferromagnetic. This is A sublattice, B sublattice. The magnetic direction is that direction. So what they will do is they will tend towards the magnetic field. They will touch, they become parallel with magnetic field, and they will start to stretch, because the magnetic field, if it is strong enough, it can stretch and work against the eta. And then at very high magnetic fields, they will be again full length. And actually, in experiment, one can also observe, I didn't prepare the slide, but what you will see is that if you go to high enough, magnetic fields, then okay, this is not the good example for that, this material, but another one, the barium cobalt germanate, there the D is around 7 times J. It's a huge number compared to the exchange coupling. In that case, if they look at the magnetization, what they observe that the magnetization goes up to a certain value, and starting from there, it will slowly go to the saturation value. So they can really observe this thing, and then the spins are stretching out. This material is different. In this case, the on-site anisotropy is much smaller. It is almost isotropic. And that's why this is very particular member of this family, which is called acamanites. Good. So then there are your friends experimentalists, and they measure different things. They can measure the ESR spectra. So this is, for example, one ESR spectrum. And what you see here is the frequency against magnetic field. Right, this is the frequency magnetic field. And this 20 Tesla, or if the field is along the Z direction, or 18, 19 Tesla, if the field is in the XY plane, corresponds to the saturation field. This is when the spins become, when they close, they canting, and they are all aligned with the magnetic field here. And the spectrum above this field is actually the excitation energies of the spins that are all pointing up, and there is a single magnon or maybe two magnons that are flipped. And that will give us these lines here. Okay. You can see that there are those lines here, and these are the usual one magnon flips. So what we are talking about is the following. So these are the three half spins, all aligned. And the field is pointing in this direction, right? Then we make an excitation. What is an excitation? Instead of having the three half, we will just turn or remove, reduce the length of one of the spins to one half in the direction of field. So this is the new state. The energy cost is proportional to G times magnetic field. Is it right? I think it is right. And there was some energy cost associated, or energy gain associated with on-site anisotropy. So there will be some number times lambda. And once this guy is here, what it can do is that it can propagate. So there will be, the Hamiltonian contains the SZ term. SZ term, we shall not forget about it. So there will be a gain in energy, because this is, if the interaction is antiferromagnetic, having these two spins parallel with each other is the largest energy. Whenever I make it smaller, I get some energy. And I think if we do the calculation precisely for the square lattice, it will be 6J, the gain in ZZ component. And since this is Heisenberg part, there will be also the hopping associated with this guy. It also gains energy with hopping, and there will be 6 times J gamma K. This gamma K is the dispersion of this object here. So what we have here, we have created a single magnon, and this single magnon can disperse. We can plot the dispersion. The gamma K, it is just the usual cosine kx plus cosine ky, like dispersion. There is a 1/2 here. Okay, so we can plot this dispersion. The dispersion, I show it where? Hello. It will be somewhere here. This is the dispersion. So it is maximal at 0, 0. It is minimal at pi, pi. And it is again maximal at, this is a cut in the Bilon zone, a pass in the Bilon zone. The pass is as follows. This is the 0, 0. From 0, 0, we go to pi 0, somewhere here maybe. Pi 0, we go here. Then from pi 0, we go to pi, pi. It is here. And then from pi, pi, we go back to 0, 0. This is the pass, and this is the dispersion of the excitation. Right. Now, this is shown in the square lattice, original square lattice of the cobalt ions. Remember that in the square lattice, we have two different chemical sites of the cobalt. So in fact, with the ESR, which usually we see only at the k equals 0 point, the ESR is a big plane wave which hits with the same amplitude all the spins. We can access not only the 0, 0, but also the pi pi because of the modulation of the tetrahedra. So there is a small residual coupling coming from the local environment that will make possible, that will make also the pi pi visible. So we have a magnon at 0, 0 and at pi pi, and we can excite both of them. And those magnons are precisely this D1 and D0 that are shown here. These are the usual magnon, single magnon excitations. You can calculate this difference here is just equals to the bandwidth of this guy. It will be 12J. Right. As we decrease the magnetic field, the energy of this magnon will become 0, and once the magnon becomes 0, it will happen at the pi pi in the Brillouin zone. It starts to condense, and that will be the onset of the Néel order. There will be a small component to the spins that are all aligned, and it will be canted in such a way that there is the added component has opposite sign for the A and B sublattice. So we can clearly understand the origin of the D1 and D0. Right. But then there is this two magnon mode. How can we see this two magnon mode? Why is it there? Okay. So let's try to understand also that mode as well. So what it would correspond to is that the ESR, plane ESR photon comes in, and via the electric and this interaction, it will induce it will have the opportunity to, it will have the S minus S minus matrix element. So what it will do, instead of plus 1/2, it will also create a minus 1/2 particle state. Right. This minus 1/2 is not stable. It can decay very easily, because if we just apply the S plus S minus on this bond, it can easily go over to 3/2, 1/2, 1/2, 3/2. We get two magnons and they can just propagate away. Okay, so in that case, we wouldn't see it, but we see it. Why? It is due to the very particular dispersion relation. So this is a cosine band. So what is the dispersion relation of two magnons? I will show you in this picture here. So what you see here is the excitation of this problem here. So on the horizontal axis is again the momentum, exactly the same path in the Brillouin zone. This here is the two magnon continuum. And what we see that at this pi pi point, the two magnon continuum shrinks to a single point. And in that case, there are some bound states appearing above it. Bound states appearing from the two magnon continuum. And actually, I would like to argue that this bound state here is nothing else but the pi pi symmetric combination of this state here. So this state is outside of the two magnon continuum, and because of that, it can be visible in the spectrum. Otherwise, when it's inside, you don't see it. Right. Why is this magnon-magnon continuum such? It is due to the square lattice that to create two magnons at pi pi momentum, one possibility is to take a magnon from 0, 0 and one magnon from pi pi. So I take one magnon from here and another magnon from there. If we add them up, I will end up somewhere in the middle. Another possibility is I take a magnon from pi 0 and the 0 pi. If I add them up, I will end up at the same energy. So any two, if I take two magnons, when the energy adds up, so when the momenta adds up to pi pi, the energy will add up to the same value if the total momentum is pi pi. So it's just a phase space constraint that will reduce the two magnon continuum to a single point here. If we have second neighbor coupling or other exchanges, this will be spread. This will spread a little bit, right? And on top, depending on the direction of magnetic field, either the bound state will above or below. So we have a bound state at pi pi. We have also the tilting of tetrahedra. The tilting of tetrahedra couples the electric field to the pi pi mode of the bimagnon of this quadrupole. In that case, it will have a matrix element which is visible in the ESR spectrum, and that is this guy here. That is this guy here. The energy is just twice the magnetic field, 2hg. So that's why the g factor is, why the slope here is twice of the single magnon modes. And the simple reason why it cannot hop is the following, that the pi pi combination of the magnons so we need to make a plane wave, pi pi plane wave of that guy. So let's just make it like we have it down, up, up, and we add with the minus sign the up, down, down, up, up, and plus, I don't need this one here, down, down, up, up. Yeah? No. So the question is, can this decay? Right. So if I apply the S plus S minus operator on these two bonds, I will get up, 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 plus up, up. Is this clear? I apply the S plus S minus here, the S plus S minus here. It will turn the minus 1/2 to 1/2, and this 3/2 to plus 1/2. This is this here. If I apply it here, and if I apply the S plus S minus operator there. Okay, we shall do the same thing here. So this will be minus. I mean, this is after application. It will be up, up, then these two big spins up, then minus. So I need to apply on this bond and this bond, the S plus S minus, and it will produce these two states. And we can see that if these two components are mixed with the opposite sign, plus minus, then this will cancel with this one. This will cancel with the one that is here. This will cancel with this one here. So if we apply the S plus S minus operator near neighboring bonds to this state, it will give us 0. This cannot decay into two magnons. Similarly, there is another combination that we may have a spin up. I mean, this is 1/2 in the C of spin 3/2. Again, in the pi-pi combination. And we can ask whether in this case, the two magnons can go away from each other. And it turns out that if they are also in the pi-pi momentum, in that case, they are also stable. They will also make a bound pair where these two spins will not dissociate from each other. And those two states are this is enlarged part, these two states that come together. This Y2 degeneracy is related to the either horizontal, that these two magnons are horizontally or vertically. Right.
So ESR couples to this because electric field couples to SS.
Yes.
And although ESR only couples to the gamma point here because of the structural distortion, it also couples.
Exactly. Yes. So there are several things that come together which make observation of this effect possible. It is very rare that you can observe the two magnon branch in the ESR, and this is such a very nice opportunity. I'm almost over, but I would like to. Well, how can we imagine this two magnon peak, this two magnon excitation? So usually spin wave is just that you have your spin waves and maybe they just start to rotate like that. In our case, it is not that. In our case, what happens is that there is a picture of it. I have even a movie, but let's first look at the static picture, and then I will put up the movie, and then I will finish, because you must be getting tired. Right. So this is the usual mode. The polarization of the spins is pointing outward of this plane. And then these are, here below, we can see just the spins that are rotating like that. This is the usual spin wave. And what we have here is that the spin becomes flat in one direction. It is like a spin quadrupole, and this spin quadrupole rotates around like this. It does not have any component that is pointing out of the z direction, which processes magnetic component. It has a quadrupolar moment that processes around the z-axis, around the axis of the z plane. Let's see if I find the animation. No, I don't need this here. Sorry. Too many things here. Animated, what is this? Yes, this will be fine if I can make it alive. How to make it alive? I need to put it into a browser. Let's see if it works. Hello? No, not this one. Okay, let's start to close these things. Because I'm anyway at the end. Good, I closed almost everything, maybe too many things. And then this here, there was the animated toolgif, and I put it into, let's put it to Firefox, it's more reliable sometimes. What's wrong? Yeah. Right. So what I do here is that I fly over the so there is this material. The red arrow is the polarization, electric polarization that shows the motion of electric polarization, and this green potato that is squashed represents the quadrupolar spin that is rotating around the axis. Good. Thank you very much for your attention. And since I'm the last speaker, I think this was a very nice school, so I would like to thank all the organizers that are here. I don't see Prabhuta is over there. Yes. So Prabhuta, Rajesh, Ganesh, and Arnab for this organizing for this wonderful school. There is one more organizer, but I don't know him, I don't see him, so maybe he will forgive us. So thank you very much. Right.
Are there any questions? You will have to demonstrate your question.
Ouch. So So maybe I was going too fast. Okay.
Good. Karlo is even for the conference, so that starts next week on Monday. So Monday
Yes.
morning, Karlo will be giving the second talk of the conference.
Right.
So thank you very much. Very nice.
Thank you very much.